Good morning, everyone. So yeah, I'll go straight to my talk. Basically, of course, my talk was machine learning for electrical power consumption data. But of course, I will focus on one aspect in this topic. And of course, specifically in this image, we have two supermarket bills and the example of supermarket bill and example of the energy bill we always receive at our home. And of course, you can see the difference between this. The supermarket bill is somehow itemized. You know, okay, if I spend 25 euro, I know maybe what percent has been spent to which item. But it's quite different from the energy bill. You just receive a bill like, okay, you need to pay maybe 200 euro. But then the bill is still, it's aggregate. You don't know, okay, how much has been, okay, maybe my TV or my fridge later has been, what is the contribution of my fridge or my TV in this bill? So in my talk today, I'll talk about, okay, how to make this electrical bill to be like a supermarket bill. That is one concept that I will talk. But two, I will talk another concept, okay, which was transforming time series signal into an image-like representation and then use advanced machine learning like convolutional neural network to facilitate now automated feature learning for different tasks like basically my talk is with these two items. So basically the title of the talk will be robust machine learning for appliance recognition in non-intrusive load power monitoring. Of course, my name is Anthony. As I'm a data scientist at CeADAR. And of course, I maintain my personal blog. At this link, you can find what I post and things like that. And the outline of my talk, of course, first, I will give you introduction to non-intrusive load monitoring or power disaggregation. And of course, then I'll go to appliance recognition. And I'll also explain about, okay, how distance matrix and CNN could be used in time series signal. And then how we have applied these techniques to facilitate appliance recognition in non-intrusive learning. And of course, I will conclude my talk with a conclusion. So let's start with the first part. Now, what is non-intrusive load monitoring? I have a short video just which give us an overview of what is NIL and how it's used. So I'll just need like a few seconds to go through and let me about it. Okay, so that's the short introduction of what's named. So basically the idea is, okay, given the you're monitoring aggregate power signal from one point source, and then you want to know each contribution of each individual appliance that has contributed that particular aggregate power signal. And of course, as we have seen from the video, this could be useful for different applications, like of course, becoming aware about how much each appliance consume, but of course, in demand side management, or it can be also used for managing appliance, for monitoring appliance or predictive maintenance in appliance and things like that. So this is a few use cases where NLM could be applied. So basically, to be able to use this, first of course, you need to monitor data, record the power consumption data at a single point source. For this to be done by using, for example, if you smart meter or just use this current or voltage sensor or smart plug, you can get this information. Of course, once you have this information, then you need to extract a unique feature which can separate one appliance from another. The fact from electrical power theory is each appliance, once turned on, has a unique signature that differentiates one appliance from another. So the idea is, okay, Once we extract this unique signature, then we can apply machine learning to learn pattern that differentiate one appliance from another. And of course, this can be done by learning algorithm. Of course, this can be supervised or unsupervised machine learning technique. And the need now can be divided into two approaches. There is event-based approach and non-event-based approach. With event-based approach, the idea is we want to disaggregate, we want to separate each appliance by first detecting events, okay, you want to detect each time when the appliance is activated, and then once you take that event, you extract a unique feature for this particular appliance, and then you classify this appliance to a specific category. But in non-events, we don't care about event, but rather we just want to match each sample we monitor from the aggregate signal to the consumption of one or more appliance. So basically, this could be you can view the non-intrusive monitoring into these two approach. And of course, basically, most non-event-based have been focused on high frequency data. It means you monitor signal at high sampling rate, and non-events has been most focused on low frequency rate, for example, that are coming from smart meter. And of course, deep learning and hidden Markov model have been one of the driving machine learning algorithm in the non-event-based approach. And of course, in event-based approach, of course, it uses hybrid techniques, both deep learning and other deep learning and non-deep learning. Of course, to get this intrusive, this event-based and non-event-based, and the example of how it could be used, I have written a survey paper, which of course just try to summarize method and techniques for non-intrusive lot monitoring. Of course, you can find more information in that particular paper. So for this talk, I will focus on event-based approach. And for event-based approach, of course, this is a process, as I said before. One, you have to monitor signal, just like the aggregate signal, and then detect events. And then once you detect events, and then you extract appliance feature that could be used to differentiate one appliance from another. And then you apply machine learning algorithm to classify, okay, maybe at this event, light was turned on, at this time, fridge was turned on. And then once you take this, then you can estimate the corresponding energy consumption. Okay, at this time, the fridge was on, then it consumed this particular amount of power. So in summary, this is the process of an event-based approach. Of course, the difference between event-based, we don't have event detection. Just you have the data and then you go on classification and energy segregation. And as I said before, with this, I will focus on event-based, but then also I will focus on appliance classification. So I will single out appliance classification in event-based techniques. Now, with appliance cognition or appliance classification, the idea is to, once you have extracted signal, you want to identify what is active appliance learning from the aggregate signal you have monitored. Of course, this is somehow challenging because you can imagine in a building, you might have multiple appliance, and sometimes this multiple appliance may share some similar electrical characteristics. For example, if you have a blender which have a rotating motor and another appliance which have a rotating motor, it means this might share some electrical characteristics. So finding an algorithm to be able to detect these two, to differentiate these two appliances might be somehow challenging. And of course, performance of existing approach is still not, of course, there are different methods which have been proposed on this particular approach, but of course the performance is not good, so much work need to be done on this particular approach. And because you need to, the appliance classification done based on the electrical feature, then finding a unique feature which can differentiate one appliance from another is an important performance factor. So what has been done? One approach has been done, of course, which is popular and as far as has been showing some success, is transforming the current and voltage signal of a particular appliance into an image-like representation, and then use advanced machine learning techniques like convolutional neural network to do recognition. So basically this approach uses voltage current trajectory. So it means if you monitor current and voltage signal of a particular appliance, and then you align current and voltage, you will get a particular shape. And this shape will be different from one appliance to another. And then you can transform this shape into an image representation, like shown in this image D. And then using deep learning, using machine learning techniques like CNN, then you can apply to classify. You can learn pattern which differentiate one appliance from another by transforming into image. Of course, this paper, of course, propose this approach. And so far, of course, the approach offer good performance, but there are some challenge. One, of course, is it's not, it failed to differentiate appliances falling under the same category. For example, if you have resistive appliance like a kettle and another resistive appliance which share the same characteristics, become challenged to differentiate appliance. So, motivated by this approach, we have been investing. How can we represent this time series signal, current and voltage into an image-like representation and then use advanced machine learning for classification? Now, we have been exploring using Euclidean distance matrix. So the idea is, okay, given a time series signal, you can find a distance between each adjacent point, and then you transform a time series signal into a high dimension 2D dimensional representation by finding a distance between two adjacent points. And then, of course, one common approach using popular is using recurrent plots. And then instead of using every information from the distance matrix, you you compress the matrix using a thresholding approach. So information, you from the value of the distance matrix into 0 and 1. It's like you're analyzing this value by using a thresholding approach with this parameter epsilon. Of course, you have a time series signal, and then of course you transform this into distance like this, and then apply this thresholding, and then you have image representation for that time series signal, and then of course you use neural network for classification or other tasks. Of course, this is one of the approaches being used, for example, in classification of in this paper where they use this approach. You just compress the distance matrix using to a current plot using a searching approach, and they apply this for activity recognition. But of course, this has one challenge, because now you are compressing this distance matrix into 0 and 1, and then in some way, somehow you might lead to loss of information, which might reduce the performance of your approach. So what we have done, one approach we have done was, okay, instead of compressing this distance similarity matrix into binary into 0 and 1, then we compress this into weighted. It means we just enforce to have, instead of having only two values, 0 and 1, we enforce to have several values between 0 up to delta. So now this data depends with the parameters. This could be depend on the performance that you want in this particular problem. So this is the idea. Of course, you extract current and voltage, and then once you have current and voltage, of course, we do this piecewise aggregate approximation now to reduce the dimension, and then of course you find distance similarities of these two current and voltage, and then you apply this compression where you compress your signal, you compress the distance matrix into you reduce the distance matrix into a low representation, into a certain range of value, but then of course not having 0 and 1, and then you apply this to a CNN classifier. And of course, we have provided this approach for appliance classification. And of course, we have we wrote a paper on this, and of course, the paper has been submitted for accepted for publication. And the idea seems to offer good performance, especially in appliance classification. And this is the idea: given the signal like this, given the input signal, and then this is the distance similarity matrix, and then you apply a weighted recurrence graph, which is compress this. Which of course you compress this distance into an image representation, but preserving the shape and the structure of the distance matrix. And this is for example, this one is the compressed one to 0 and 1. Of course, as you see, you are missing some of the information because this one maintains the shape. So what we propose, of course, instead of going to this 0 and 1, you compress the distance matrix into a representation while maintaining the shape of your distance matrix, and then use this as input to your model. Of course, we tested this for appliance classification on submitted datasets on 3 different datasets, and of course, we compared this approach with the state-of-the-art approach using the voltage current trajectory. And of course, we found that our approach offer good performance, of course, improved performance compared to the VI trajectory. But there is 2 limitations. One, this approach had 2 parameters, delta and data and this epsilon. It means before you use this, you need to find what are the base parameters you can use to transform your time series signal into image representation so that you get good performance. But 2, we test this approach only on a smart submitted dataset. In actual fact, if you need to apply these techniques in the practical situation, you'll be monitoring the aggregate signal. So to address this limitation, we proposed another approach, which is known as adaptive weighted recurrent graph. So the idea is, with this approach is, okay, the first idea, we introduced 2 parameters, but okay, can we integrate this parameter as part of the deep learning pipeline? Okay, while learning the weights of the deep learning, can we also learn the weight of this parameter? Can we consider this parameter as weight of the model so that so that the model can learn which parameter will give good performance instead of treating them as hyperparameter? So we provide a adaptive weight this pipeline in deep learning. So you just pass your time series signal like this one, and then this will go into the this block, and of course it will generate the adaptive weighted recurrent graph, which of course will be used for classification. So we proposed this approach, and we submitted a paper under IEEE Smart Grid, which is under review, and then we tested our approach on aggregate submitted data. Now, if you go on the aggregate data, the question is, how do you obtain this signal from aggregate signal? So what we did was, of course, first you monitor events like this. If you detect events, you extract the current signal before and after events, and because current have an additive properties, and then you subtract the current after and the current before. So for example, this is current before, this is current, D is current before, E is current after, and then if you take this minus this, you will get the current which has the activation current. It means this will represent the appliance which has been activated, and then you transform this into image-like representation using the adaptive weighted recurrent graph, and then you use CNN for classification. Of course, we tested this into 2 datasets. One, industrial datasets, where we wanted to classify industrial machines, which is the 3-phase power signal. You have 3-phase motors, single-phase motors, and other residential appliances. And also we tested on aggregate data monitored in residential building. And of course, we get good performance. As you can see, if you compare it to VI trajectory, for example, this was in the residential data, and this is the industrial data. You can see, of course, if you see the coefficient matrix, the number of positive and false negative is much reduced on the proposed approach compared to the VI trajectory approach. Of course, despite the fact that this approach gives good performance, but it has 2 limitations. One, you assume that you have only 1 appliance is active at a time. Of course, this might hold if you are monitoring, if you are recording signal at a very high frequency, but still there might be a chance you might have more than 1 appliance running. But 2, this requires a perfect event detector, because remember, to get the appliance feature, you need to extract currents before and after events and then do subtraction. So if you miss the event, it means you never get the good current signal to represent for future representation. Now, this is one of the limitations that we found for this particular approach. To overcome this, we proposed another approach, which is which apply Fry's current decomposition and multi-level learning using convolution neural network. So the idea is, instead of assuming that only 1 appliance is learning at a time, of course you allow, okay, you can have more than one appliance running at a time. So the task now is to classify detecting multiple learning appliance from the aggregate signal you want from a single point source. So for example, at this particular point, you have only one appliance, but at this particular point, you have two appliances running, and then you might have more than one appliance running at the same time. So given this information, given only the activation current, can we detect more than one appliance running at the same time? So what we do, of course, in this particular approach, you just monitor current and voltage, and then you decompose the current using the fringe power theory. You decompose the current into two components, active and the inactive component, and then you transform this active and inactive component into distance similarity function, which of course will give you image-like representation, and then use CNN for MATLAB learning learning classification approach. Of course, we had done this particular approach, and we submitted a paper on which, of course, is under review on MDPI Energy Journal, and we tested this on aggregate signal. And this is the idea, of course. You monitor the current signal, and then you decompose this current into two active and the inactive component. And what you can see from this, it means even for appliances which share the same, which is near similar current signal, then the decomposed current, especially the inactive component, will be different. And this can help you now to differentiate multiple learning appliances. And of course, you signal into using a distance, Euclidean distance matrix, and then you use this image to feed into convolution network for classification. Now, because this is MATLAB learning, which is quite different from the normal multi-class or binary classification, we use softmax sigmod, contrary to we use softmax activation function, which contrary to the most used sigmod activation function, which of course, if you use sigmod, then this will enforce you to have to, of course, to find the threshold to get the predicted level. And of course, in the way this helps us to model the relation between multiple learning appliances. So we tested this approach and compared to other different state-of-the-art approach. And of course, we found that the presented approach offer good performance compared to other approach, and of course, which give us high performance score. And of course, this is example visualization for the prediction. For example, if you just use the current signal, this is, for example, the true is what there is 3 appliances running at this time, and then you want to detect all these appliances running. And then if you just use current signal, this will give you, or will be able to detect only 2 appliances. But if you decompose this into active and reactive, then you'll be able to detect all the appliances. Or if you use only the VI trajectory, it can only detect 2 appliances. But if you decompose and use the distance similarity matrix, this can detect all the 3 appliances. So basically, what we have been doing as part of the NIL, especially on the appliance classification, that we found that, of course, representing the time series signal, the current signal into image-like representation, of course, allow you to exploit the power of CNN, computer vision, for future representation and learning, of course, for multiple, for different other applications. We have tested this approach only for power signal, current signal, but we believe this could be also used for other applications. So to conclude my talk, so of course, my talk has been focused on appliance recognition using non-intrusive load monitoring, and of course, most existing work in non-intrusive load monitoring have been focused on only providing disaggregated power. But I believe that, okay, this technique could be combined with other techniques to facilitate added value services in smart grid or smart power environment. For example, one could explore how can we use these new techniques for example, to do like automated predictive maintenance, especially in industrial environment where you have heavy machines. By monitoring these appliances, it's possible to explore this particular application. By two, the proposed approach of representing this signal, time series signal into image representation, and especially the approach which integrates this as part of the end-to-end pipeline with deep learning could be explored for other application in time series classification problem. Of course, I said before, we have tested this only for for current signal, but we believe this could be used for other application. Yeah, so that's end my presentation, and I would like to hear if there's any question on that particular. Thank you very much for your time.